Hello 111 students. I got a request for a video on oxidation numbers, so let's take a closer look at them today. Oxidation numbers are a way to track how many electrons an atom owns as compared to how many it would own as a free atom. When do we use them? Well, we use them to identify reduction and oxidation processes in redox reactions, as you saw in Chapter 8, and to identify more stable and less stable Lewis structures. These are very analogous to formal charges. It can be helpful to think of oxidation numbers as existing on a number line. If you are moving in a more positive direction, this represents a loss of electrons, which is oxidation. If, on the other hand, you are moving in a more negative direction with your oxidation numbers, then this represents a gain of electrons, which is reduction. But how do we determine oxidation numbers? To begin with, pure elements always have an oxidation number of 0. This is the free reference state. For a molecule or ion, the sum of all the oxidation numbers must equal the charge on it. For neutral molecules like acetone or a formula unit of a salt, the sum is 0. For ions, the sum is the charge on the ion. Now we can look at a couple of elements that have set values that we can rely on. The oxidation number of fluorine is almost always -1. The oxidation number of hydrogen, however, is almost always +1. But there is one exception. If hydrogen is bound to a metal, for instance the compound sodium hydride, it is -1 instead because the hydrogen is behaving as the anion. The oxidation number of oxygen is almost always -2, but this has two exceptions. If the oxygen is bound to fluorine, then its oxidation number is +1 to balance out the fluorine. And if the oxygen is bound to oxygen, not as a free oxygen molecule, but as a peroxide, then its oxidation number is -1. To determine the oxidation numbers of other elements, start with the set elements, fluorine, hydrogen, and oxygen, and go from there. Let's look at some examples. Throughout the rest of this video, you can hit pause and try to work out the answer before I give each of them. Our first example is sodium chloride, simple table salt. Sodium chloride is made up of two ions, sodium plus and chloride, which has a -1 charge. For monatomic ions like sodium and chloride, the oxidation number is equal to the charge. So sodium's is +1 and the chlorine's is -1. These also add up to 0, which is also the overall charge on 1 unit of sodium chloride. Our next example is iodine, I2. Since this is a pure element, its oxidation number is 0. Let's look at something that's a little more complex. Carbonyl fluoride is a very toxic, very dangerous organic compound. The oxygen in this compound is one of our set elements. Its oxidation number is -2 according to the rules. Fluorine is in a similar boat. Its value is -1 according to our rules. The overall charge on this molecule is 0. It is neutral. Therefore, the sum of all the formal charges must be 0, and this lets us work out what carbons must be. So we say that 0 equals carbon plus 2 times -1 to account for the fluorines, and plus a -2 for the oxygen. If you crunch those numbers down, you find that carbon is carrying an oxidation number of +4. Our last example is dichromate, Cr2O7 2-. This is a very common polyatomic ion and a potent carcinogen. Again, oxygen is one of our set elements, with a value of -2 according to our rules. The overall charge on this ion is -2, therefore the oxidation numbers must add up to -2. So we set up an expression saying that -2 equals 7 times -2, to account for the oxygen, plus 2 times the chromium, because there are 2 chromium atoms present. If you crunch those numbers down, you find that chromium must be carrying an oxidation number of +6. Well, there you go. That's oxidation numbers. I hope that answered a few questions that you had, but if there are any more, please feel free to come to my office hours or hit up a study pod.